Hi to everyone. Can you hear me?
Yes.
Okay.
Start
Let me try.
sharing to see if everything works.
Yes. So let me try to see if it works. Okay. Normally you should be able to see my screen.
Yes, looks. Well, now I see myself also.
Okay.
Are you okay with being recorded?
Yes, sure.
Okay, let's see where we are with time. Yeah, maybe we start.
Okay.
Okay, our last speaker for today is Francesca Pratali, and she will be talking about the root functor.
Yes. So first of all, thanks for the invitation. And I would like to say that Ithaca is really it was the first door that I had to category theory as an undergraduate student. So I'm very happy to be here and to talk as a PhD student. And okay, so today I'm going to talk to you about what I call the root functor. And so it is something which concerns operads, infinity-operads, and localization, and the interplay between discrete operads and infinity-operads. So there is going to be an introductory part, and thanks
yes,
to...
Francesca, if you want, you can hide my face from the slides.
Oh, sorry. Okay, yeah. And okay, so thanks to Vova for their talk, because it's also quite useful because it has some intersection with what I'm going to say. And so maybe I'm going to start very quickly by recalling what are infinity categories, like vaguely. So infinity categories, we can see them as maybe also a semantic framework where the equalities in the axioms which define a category, so associativity, composition, and unitality, are replaced by homotopies. Okay, so this is the leitmotif. Then how do we model infinity categories, where there are several models, and the one we choose, like I chose to present today, is the model of Joyal quasi-categories. So basically, Joyal's model is based on the category of simplex delta, whose objects are finite linearly ordered sets, and where morphisms between any two such objects are just functors of cosets, so non-decreasing maps of orders. Okay. Any such category, the simplex category delta is a subcategory of categories, essentially by definition, and this allows to define a nerve functor, which basically allows to embed the category of categories into the category of simplicial sets, which we define to be the category of presheaves over delta. And how do we do this? We take a category C, and then we realize it as a simplicial set via its nerve, and the n simplices of the nerve of C are going to be the set of morphisms in categories from the poset N into C. What does this mean concretely? Well, an element in this, sorry, this is too big, but an element in this set is going to be just a string of n composable morphisms in C. So basically, we are labeling the poset. We're labeling the objects with objects of C, and the arrows with arrows of C. Great. So first of all, let's notice that this nerve is fully faithful, so we can do category theory inside the simplicial sets. And how do we weaken the axioms of a category? Well, the pattern is always the same. We consider this nerve functor, we study its essential image, we characterize its essential image, and then we weaken the condition. And that's how one gets to the definition of a quasi-category. So yeah, so what is a quasi-category? A quasi-category is a simplicial set which has the right lifting property with respect to what are called the inner Horn inclusions of simplices. So I'm not going to say what these are specifically, but these are just combinatorial objects which ensure that there exists a composition which is well defined up to homotopy, and that all these homotopies are coherent one with the other. So for example, if we consider this inner horn given by lambda to 1, a map from lambda to 1 into X has the shape of two composable morphisms, and the existence of a lift means that we can actually compose these morphisms, and that these morphisms and that this composition is witnessed by an homotopy, what we call sigma. Okay, so this is the general setting for infinity categories. Let's move to operads. So what is a discrete operad in the first place? So the way we are going to read discrete operads today is as discrete multi-categories. So an operad is like a category, but morphisms are allowed to have multiple inputs instead of just one. So a discrete operad is given by a set of objects, and then for any choice of objects, x1, xn, y, we're going to have a set of operations from x1, xn into y, which we can depict in this way, where the vertex denotes the operation, basically. And then, well, in a category, we have the composition law for morphisms. And in this case, we have a composition law for multimorphisms or for operations. What does this mean? Well, whenever we have two composable multimorphisms, which means that the output of one is the same as the input of the other, then we can compose them. This means that we can identify the output of one with the input of the other and get another operation. Great. Then there are some other axioms, which are just like an action of the symmetric group on all these sets, which mimics the composition, the permutation of the variables. And then we have a unit, so every object has an identity element. And then there are axioms of associativity, unitality, and equivariance of the partial composition, where equivariance is with respect to the action of the symmetric group. Okay, so maybe let's just see an example so that we build some intuition. Whenever we have a symmetric monoidal category, we can build an operad which has as set of objects the same set of objects as V, and where multimorphisms from x1, xn into y are just given by morphisms from the tensor product of the inputs into y. So that's why we say that symmetric monoidal categories are also representable operads, in the sense that, well, this set of morphisms can be represented by the tensor product of the input elements. Okay, of course, there are more general elements, but whatever. Okay, so as, to define infinity-operads, we have the same guiding principle as for infinity categories. So in an infinity-operad, morally, the equality in the axioms, in the defining axioms, are replaced by homotopies, which have to be coherent, like coherent one with the other. And in particular, this means that partial composition is going to be defined only up to homotopy. Again, this is the philosophical principle, but then one needs to give a concrete realization of such infinity-operads. And again, there are several models for this. And the model I'm using today is an extension of Joyal model for infinity categories. And it's due to Grothendieck, and it's called the model of quasi-operads. So, and please note the parallelism with what we did so far for infinity categories. So this model for infinity-operads is based on a category of trees, omega, so whose objects are finite rooted non-planar trees, okay? And where morphisms are defined as morphisms between the operads generated by a tree. So by definition, so let me write it in, so by definition, a morphism from T into S in omega is a morphism between the discrete operad generated by T into the discrete operad generated by S in the category of discrete operad, where omega is an embedding of omega, well, sorry, too many omegas, but where omega is an embedding of the dendroidal category into the category of discrete operads. Okay. If you're curious about who is this operad, we can talk about it later. Now, I'm just going to give as as an assumption that this kind of looks familiar for you. And well, okay, so we can define then dendroidal sets as the category of presheaves on this tree category. And as it happened for simplicial sets, the fact that we have an embedding of omega into operads, it allows to define a fully faithful nerve construction, so what we call the dendroidal nerve functor, which embeds operads into dendroidal sets. So we can do operad theory inside the category of dendroidal sets. How is it done? Well, exactly in the same way. We take an operad P, and then we build a presheaf, which we call dendroidal nerve of P, whose value on T are the sets, is the set of morphisms of operads between, well, the operad generated by T into P. Okay, again, one looks at its essential image, characterizes it, and then weakens the defining property, and that's how one gets to the definition of quasi-operad. So a quasi-operad in the dendroidal set, a quasi-operad is a dendroidal set who has the right lifting properties with respect to what are called dendroidal inner Horn inclusions. So these are tree-like generalizations of these inner Horn inclusions that were used for simplices, but which take into account the fact that now we not only have morphisms with one input and one output, but several inputs and one output. Again, let me take this notion as a black box, and let me just do an example. So if we consider a tree of this shape, then we have its inner horn lambda et. There is only one such horn. It is relative to this inner edge of T, and it is given by the union of the two pieces of T determined by E. Okay, cutting T, we cut T in a half, and we have two subtrees. Okay, so this map here from the horn of T into X is basically selecting two composable operations in X. So an operation whose output coincide with the input of the other, with one input of the other, and the existence of such a lift, of such an extension, ensures the existence of a bigger tree who is going to give us our operadic composition. Okay, and okay, so this is the defining property of a quasi-operad. Great, and okay, so maybe let me just say this. This theory generalizes the theory of simplicial sets in this way. So let me start from here. So as any category is in particular a multi-category, trivially, we can embed delta into omega. So we can embed the category of linear orders into the category of trees by realizing every linear order as a linear tree, basically. And this embedding, so this inclusion, makes all these diagram comments. So we have well, this is what we were saying just before. So we really have an extension from the theory of categories to the theory of operads. Also, the theory of dendroidal sets extends the theory of simplicial sets. And well, these two, like the composition of the inclusion with the nerve gives the unit embedding. Okay, these are some very nice properties that the one who wishes to have for infinity-operads. Okay. Now, okay, so now so now this is the definition of quasi-operad, so operad up to homotopy. Actually, we don't talk just about quasi-operads, we talk about the homotopy theory of quasi-operads, or more generally about infinity-operads. What does this mean? Well, it means that basically, thanks Vova, like we put a Quille-model structure on the category of dendroidal sets, and we realize quasi-operads as the fibrant objects, so the objects which are homotopy invariant in some sense. And well, the homotopy theory of quasi-operads or infinity-operads, if you wish, is equivalent to the homotopy theory of operads enriched in topological spaces. So it's like, by this very combinatorial construction, we have actually modeled the homotopy theory of operads enriched in topological spaces that we consider up to weak homotopy equivalence. Okay, and this is very important. Like this is why the theory of infinity-operads is relevant, in domains like algebraic topology or algebraic geometry and homotopy theory more generally. Okay, now I will start writing, and okay, now we start writing, and here it comes the part of my results. So basically what we've seen so far is that, okay, we have discrete operads. So where basically the sets of multimorphisms are indeed sets, okay? So the spaces of multimorphisms are sets. And then we have infinity-operads or quasi-operads. I'm going to call them, like I'm going to confuse these names. And okay, and the idea is that by the equivalence of homotopy theories that I was telling you before, the idea is that for an infinity-operad, for a quasi-operad, the space of operation from x1, xn into y is going to be really a space. So a topological space, which means a simplicial set, like a Kan complex, but whatever. Okay. Well, what are the differences between the two? So this model, so discrete operads, is a rigid model, okay, because we are using equalities. So yeah, so we're using equalities, and the relations we establish have to hold on the nose, while this model of infinity-operads is pretty flexible, because we only allow, because we only care that two things are the same up to homotopy. So this is quite a flexible notion, right? On the other hand, these are easy, like discrete operads are easy, more or less, because there are no homotopies, precisely for the same reason. Well, they're rigid, but they're easy because there are no homotopies involved. And on the other hand, infinity-operads are, well, they carry a lot of homotopical data. So carry lots of homotopy coherencies. So what I was interested in is understanding the relation between these two classes of operads, and to see whether whether arguments on infinity-operads can be reduced to arguments for discrete operads, which may simplify many computations in concrete applications, for instance. And well, it turns out that there is a way to produce an infinity-operad from a discrete operad. So let me do this. So whenever we have P a discrete operad, whenever we have P a discrete operad, and whenever we have S a choice of what we call weak equivalencies in P, so morphisms from an object X to another object Y, that we declare to be weak equivalencies, we may be interested in looking at a new operad P where the arrows in S are inverted, right? So we're interested in the localization of P at S. And this yields no longer a discrete operad, but an infinity-operads, because the localization is a process which, I mean, it's quite complicated, but inverts the arrows, and there are many relations which hold up to homotopy. So we can localize, so localization, we can apply localization and obtain an infinity-operad, which we are going to call, in this way. Now, the question that one could ask is the following. So we have this diagram. Let me make it a bit smaller, if I manage. Yes. Okay, so we have this diagram: discrete operads, infinity-operads, their differences, and how they interact. Given a discrete operad with a choice of weak equivalencies, we can produce an infinity-operad by localizing these weak equivalencies. And the question, like a very natural question to ask, is, does any infinity, or every, maybe every, Does every infinity operad arise as the localization of a discrete operad? Of course, I mean, this question is pretty important because it really allows not only it really connects deeply the theory of infinity operads to the theory of discrete operads by means of one only operation, like localization. And well, remark, for categories, the answer is yes. Every infinity category is equivalent to the localization of a discrete category. So for infinity categories, the answer is yes. And this is due to Joyal, Stevenson, but then in a much stronger form, which I'm not going to talk about today, but also by Barwick-Kahn. And the answer that I would like to give you in the next 10 minutes is that the same is true. The same is true also for infinity operads, and this is what I call the root functor does. So theorem. Every infinity operad is equivalent to the localization of a discrete operad. And moreover, actually, what we're going to do is not only proving that every infinity operad is equivalent to the localization of a discrete operad, but we're going to explicitly exhibit this discrete operad and the maps we're localizing at. So we have also an explicitness. And yeah, so every infinity operad is equivalent to the localization of a discrete operad, and moreover, we can construct actually a section of localization. So we have a functorial way to associating to every infinity operad a discrete operad, which is equivalent to the original one after localizing. So and moreover, we have, we can exhibit, let me say a bit vaguely like this, we can exhibit a functor, we can exhibit what I call this, a section of the localization functor. Of course, all of this that I'm saying is to be understood like in infinity categorical terms, like a localization of infinity category, like a section in an infinity categorical way, etc., etc. Okay. So maybe in in the time that remains, I'm going to give you the proof of this theorem, very like in a sketchy way, but still quite explicitly. And then if I have time, and this is something that is work in progress, and that's why I would like to talk to you about this, because maybe you know much more than me. Like, I discovered that the construction that I gave, the proof that I gave to this theorem is particularly linked in the categorical case to a construction due to Cisinski, which is called décalage, categorical décalage, and which is connected to Grothendieck proper functors. And yeah, I would like maybe to spend 1 minute or two on this connection just to see where it can bring us in the operatic case. Okay. Do you have okay? So no, wait. I just only have other maybe 5 minutes, so questions at the end. Okay. So how do we do this? So first of all, okay. So proof. So how do we prove the theorem? Okay, we said that our infinity category, like our infinity operads, live in dendroidal sets. So what we do, so the first step is that we construct a functor, so a real functor, which goes from the category of dendroidal sets into the category of discrete operads, and which associates to any dendroidal set X a discrete operad omega over x. So discrete operad, which we call the operad of elements of x. So the operad of elements of x. So basically, the objects of omega over x are the elements of x as a presheaf on omega. So what does this mean? They are couples T3 and alpha amorphism from the unit of T into x. But a nicer way to express this, what are the elements of x? They are trees which are decorated by objects of x on the edges and by operations or multimorphisms of x on the vertices. Okay, so they are trees of this form. So here we have x1, xn. Here we will have like a p1 maybe, p2, p3, where the xi are objects of x and pj are operations. Operations in x, okay? Great. And then what are the multimorphisms in omega over x? So I'm writing very big again. So okay. And so what are the multimorphisms? So the multimorphisms, well, the multimorphisms are defined in terms of maps of trees which satisfy some independency condition. So a multimorphism from, so maybe a multimorphism from T alpha 1, T1 alpha 1, Tn alpha n into S beta is just going to be given by a map from the disjoint union of T1 Tn into S, which commutes over X, which satisfies some property, like which is wide and independent. These are some conditions. Okay. Now, okay, so what we did is constructing a functor from dendroidal sets into operads, right? So we have our operad of elements functors here. And we said that the category of operads can be realized inside dendroidal sets by its nerve. So we can actually consider the composition given by dendroidal sets and then the nerve. Okay. And okay, and what we see is the following. So remark. So given an object T alpha of omega over x, which corresponds, as we said, to a tree labeled by objects of x, there is a canonical way to associate to an object of omega over x an object of x. What is it? It is considering the element which labels the root of the tree. Observe that this is the only canonical choice that we have, because otherwise, like, we have many edges and we don't have like maximal elements. We only have a minimal element, which is the root. So given an object T of alpha, or T alpha of omega over x, we can produce y, so the objects, an object of x, and proposition this extends to a functor of dendroidal sets from the dendroidal nerve of omega over x into x. This proposition involves checking some left can extension property. Like we extend basically co-continuously in some way this morphism. And okay, so proposition, there exists this functor. So definition, the root functor, and I'm going to finish soon. So the root functor is precisely, so the root functor of a dendroidal set X is precisely this evaluation at the root. So it is this morphism. It is this morphism from the nerve of the operad of elements of X into X. And basically, well, the theorem consists in proving that it is precisely this root functor which exhibits X as the localization of omega over X at the preimages of the identity. So if we call, just to conclude, if we call, J the preimages of the identities of X, we have, of course, an induced map from the localization of the nerve of omega over X at J into X. And this map is a weak equivalence of infinity-operads. And okay, maybe one last comment. This result extends Joyal result for infinity categories. In what sense? So corollary, when X is a simplicial set, the operad omega over X is actually the category of elements of X. So this is the category of elements. And the root functor consists in evaluating, and the root functor consists in what is known as the last vertex functor, which maybe you're familiar with. That is just the evaluation of a simplex at the last vertex. So corollary, this is a theorem of Joyal, basically. And okay, so let me just write this and then I'll finish. So definition. So this is the theorem. And corollary, this is due to Joyal. So when X is a simplicial set, this operad is actually a category. It is the category of elements, and the root functor is just the last vertex functor, which goes from the nerve of the category of elements of X into X, and which sends an n simplex of X into the evaluation of the last vertex. And yeah, I'll stop here. No speculations. Thank you.
And open up the floor for questions or comments. Feel free to unmute yourselves.
May I ask a question about the formulation of the theorem? So if you go back, you said that there is like a section of the functor, but right. So you have op infinity and you have op. You obviously have inclusion functor from op to op infinity, and you say that there is a section. But
yeah,
what
okay,
I'm confused about, well, so like, you know, on the left hand side, the mapping spaces are not discrete. If there was like an actual infinity categorical section, then, you know, on all mapping spaces, it should also be like.
Yeah, no, definitely. So I was very imprecise. So thank you. So I can be a bit more precise. So, well, let me rectify this. So the correct thing is that we can exhibit a section of the localization functor. Now, the localization functor is not a functor which goes from the category of operads into the category of infinity-operads, but it is a functor which goes from the category of operads with weak equivalencies, so what are called the relative operads, into the category of infinity-operads. Because of course, like given a discrete operad, you need also to be given the set of maps at which you're localizing. So the root functor, so this construction of the operad of elements and the root functor, they give a section in this way.
And you view the left-hand side as an infinity category as well.
And so I view the left-hand side. I look at the left-hand side as a one category for the moment.
As a one category.
Yeah, and what I'm working right now is proving that actually this localization functor and the root functor. So let me maybe write relative operads. So what I'm working on right now is proving that the localization functor and the root functor establish an equivalence between the infinity category of infinity-operads and the infinity category of relative operads obtained by localizing relative operads at Joyal-Canwick equivalencies. Now, this should be true. It is true for infinity categories, and I think I have an almost proof for infinity-operads. But yeah, but you need to have the equivalence, you need to localize. Sorry, you need to localize at Joyal-Canwick maps. Yeah. Thanks for the question.
Anyone else?
Can you say a few words about what the localization of an operad at a set of maps is?
Thank you very much, because actually, like, I had to define this localization because, yeah, but definitely. So let me say that there are two ways of defining localization. So there is let's say, so there is a model independent way, you know? Like, by now we know that there is up to equivalence of infinity categories, one like a unique infinity category of infinity-operads. So we can work with that. And we can give the definition of localization by means of the usual universal property. Like we can say that we take P, an infinity-operad, we take S like a subspace of one morphism. It's okay, like subspace of one morphisms. And then the localization of P at S, what is it? It is a map of infinity-operads with the following property, such that for any other infinity-operad Z, the induced map from, let's say, mapping space from P S minus 1, yes, Z into map P Z is fully faithful, and the essential image is given by precisely those maps from P to Z, sending S into equivalencies. Okay, so this is like the abstract definition with the universal property. It's like what we want to model. However, and then you can say that abstractly, this localization always exists. So also remark, P, the localization of P exists because we can consider P S minus 1 given by like the like we can make a push out, like we can like an homotopy push out and formally invert the arrows in S. Okay, so this is the definition. However, this definition is not super useful if we like, yeah, whenever we work with a concrete, yeah, so this is the point. Whenever we work with a concrete model of the infinity category of infinity-operads, we need to implement this construction. And this construction is not easy to implement in general. For example, for simplicial operads, we do not have like a notion of localization which is not abstract for the moment. And in dendroidal sets, so in the model of dendroidal sets, I defined a notion of derived localization. So localization derived with respect to the operatic model structure, and which satisfies an analogous universal property. And then I provided a model for this. But it is true that, so maybe what I can say is that whenever, like when you choose, so when you choose a model for the infinity category of infinity-operads, you need to implement localization in that model. And I mean, with dendroidal sets, it's not super surprising. Like, it's really, the definition is given by means of the same universal property, and then you prove that for a dendroidal set, which is like a cofibrant, so which is normal, this push out actually works. But you need to, yeah, you need to work a bit.
Yeah, thanks. I suppose I find it surprising, just naively. So one morphisms are one-ary operations, right?
Yes.
Yeah, I mean, unless the operad is representable, right? It's more needle one category. I mean, the higher operations are not determined by the one-ary operations, right? So
no.
so and all you do change here are the one area operations, right? That's the only thing you localize it.
Yes.
So I kind of find it surprising that you can get every infinity operad by just basically taking an associated one operad and then only doing something with the one area operations. Right?
Yeah, but okay, but let me say, I mean, yes, okay, yeah. I mean, it is surprising maybe as a result, it's true, but it is not true that like unary operations do not influence like n-ary operations, because for example, like, I don't know, like if you have an n-ary operation and you have a unary operation, you can always form another n-ary operation by, I mean, in several ways, no? Like a unary operation is going to be like this, and you can either decide to put it here or decide to put it here, whatever, okay? So you do in, like you do produce new operations with this, and inverting, and basically, yeah, maybe visually it's better even, because inverting a unary operation allows you to identify maybe this unary operation, n-ary operation with this, for instance. So it does affect the n-ary operations. Yeah, then it's, yeah, I don't know, yeah, then it's still I mean, yeah, I don't know if I can say something more than this, but
Yeah, no worries at all. Thanks anyway.
yeah. But also maybe something that I can say is this, like, sorry, this result, so this localization result holds for sigma-free operads. So there are some operads for which this is not true. Maybe this is not very surprising, but like for the commutative operads, like if one does the example, this doesn't work. So maybe for X to be equivalent to the localization of its operad of elements at something, we need X sigma free. And so this rules out some operads, but in homotopy theory, in any case, we don't really care. So